In this video, we're going to discuss the rules for the quantum numbers that quantify the energy of an electron in a bound into an atom. Now, the previous section talked a bit about the Zeeman effect, and we won't go into much detail with that here, just that the Zeeman effect showed that there's a magnetic field associated with the orbit of an electron around an atom and the spin of an electron on its own axis. So think of an electron orbiting an atom like the orbit is like a little wire, and the electron is a bit of electricity going through the wire. That creates a magnetic field. Additionally, if the electron is spinning, a charged object that's spinning, it will also create a magnetic field. So there are 5 quantum numbers that, when put together, allow you to discuss the energy state of an electron. The electron has to be in one of these configurations limited by the 5 quantum numbers available. And the first quantum number we've come across before, the principal quantum number. It most closely associates the energy of the electron in the bound state of the atom. The principal quantum number, lowercase n, is often used. It has to be some positive integer value. N equals 1, 2, 3, 4, etc., up to however big you need to go. N equals 1 is the ground state. N equals 2 is the first excited state. N equals 3 is the second excited state, and so on. Second number, principal quantum number, is the angular momentum quantum number given by a lowercase l. You're limited here for allowed states of the angular momentum depending on the principal quantum number. So the angular momentum quantum number, this lowercase l, it goes from 0 in integer steps, 0 to n minus 1. Those are the allowed states. So the range of states allowed for the angular momentum quantum number, L, depends on n. If n is equal to 1, small l has to be 0. It cannot be any other option. If n is equal to 2, small l is 0 or 1. If n is equal to 3, small l is 0, 1, or 2, and so on. So the range of available angular momentum quantum numbers depends upon the principal quantum number. Now the angular momentum quantum number, L, you can find the total angular momentum of the system if you know what this angular momentum quantum number is. You just plug it into this relationship, where the total angular momentum is equal to small l times the quantity small l plus 1. Take the square root of that and then multiply it by Planck's constant over 2 pi. Note that it is possible in atoms for an electron to have 0 angular momentum, which, if you think about it, an electron in orbit around something shouldn't have 0 angular momentum, but this is the quantum world we're talking about. Now, angular momentum can be projected along some axis, some z-axis, when we measure it. So the angular momentum projection quantum number, m sub l, depends on the orientation of the angular momentum, and there are only certain allowed states available. M sub l has to range from, again, in integer steps, from minus l to plus l. So if l is 0, m sub l has to be 0. If l is 1, m sub l can be minus 1, 0, or 1. If L is 2, m sub l could be minus 2, minus 1, 0, 1, or 2, and so on. The projection of the angular momentum L sub z is just this angular momentum projection quantum number m sub l times Planck's constant over 2 pi. So L sub z and L are just to give you the angular momentum. Those are not quantum numbers. They depend on the quantum numbers n, l, m sub l. And then finally, 2 more. There's the spin quantum number, S, which depends on the type of object you're talking about. For electrons, it's 1/2. Photons, it's 0. It depends on the particle. But we're going to talk about electrons because we're building atoms in this next video. So we need to talk about how electrons are bound into an atom. The spin quantum number is 1/2, always. And since it's always 1/2, it's not a useful address for addressing where an electron is in an atom, because it always has to have that value it's kind of redundant to use it when talking about assembling electrons in an atom, and we'll see that we will skip it when we talk about the electron's address. But the spin quantum number allows us to understand the spin projection quantum number, m sub s, which is plus or minus the spin quantum number. Well, the spin quantum number is 1/2, so m sub s for electrons has to be plus or minus 1/2. That's it. And again, we can talk about the spin projection, s sub z, in the z direction is equal to the spin quantum number 1/2 times h over 2 pi. Again, s is given as 1/2. So we have 4 real quantum numbers that we need to worry about when we talk about the atoms that you'll need to consider. We have the principal quantum number, angular momentum quantum number, angular momentum projection quantum number, and spin projection quantum number. So n, l, m sub l, and m sub s. So an electron is going to have some orbit, some address dealing with those 4 quantum numbers. Again, spin quantum number is 5. It does have 5 fundamental quantum number, but for electrons, that's just 1/2. So since they all have spin 1/2, we don't have to worry about it.